Okay, thanks, Heike. I want to thank the organizers for inviting me to this very nice conference. It's been a very long time since I was last in Budapest, so I'm very happy to be back. Okay, so this talk is going to be similar to the talk I gave in Oberwolfach in February. So those of you who were in Oberwolfach will be familiar with what I have to say. But there are many people in the audience who were not there, and the composition of the audience is slightly different. So I decided to present a lot of background and definitions, and I will also try to state the questions that were sort of the motivations for our work. I should say this is all joint work with Saharon Shelah. So I'll try to present the motivating questions. I'll try to explain as much as possible the motivations that led to this work. Okay, so what I'm going to talk about is a new method for proving consistency results about cardinal invariance. The nice thing about this method is that it sort of works both at omega and at arbitrary regular cardinals, including uncountable regular cardinals. Okay, so you get sort of uniform proofs in some cases of consistency results that work for any regular cardinal, and it's based on the method of Boolean ultrapowers. Okay, so I'm actually not going to try to give any proofs, but I will hopefully give all the relevant definitions and state all the relevant theorems necessary for the applications. And then there are lots of open questions, so I will end with many open problems. Okay, so so we've seen definitions of cardinal invariance many times. Mostly they were at omega, but you can also define them at any regular cardinal. So I'm going to be assuming throughout the talk that kappa is some infinite regular cardinal. I've tried to put this requirement on all the slides, but if I forget in the future, kappa will be an infinite regular cardinal. So we have this eventual domination ordering for two functions from kappa to kappa. So f is less than star below g means that the set of places where this inequality fails is small. So you look at the set of alpha less than kappa where f alpha goes above g alpha, and that's a small set that has size less than kappa. And a subset of kappa to the kappa is bounded if there is a function g from kappa to kappa which is above everything in the family f. That should be the same f as that. F is unbounded if it is not bounded, and f is cofinal means that, it's cofinal in this ordering. So given any function from kappa to kappa, there is one in the family which is above it. So you have the two cardinal invariants associated with these notions, that the two basic cardinals associated with this notion. So B kappa is the smallest size of an unbounded family, and D kappa is the smallest size of a cofinal family. Okay, so now I'm going to move to almost disjoint families. So I'm going to define 6 invariants, okay, but I'm not going to necessarily have time to talk about state results on all 6 of them. So this is almost disjoint families. So you have two subsets of kappa of size kappa. They're almost disjoint if their intersection has size less than kappa. An almost disjoint family is a collection of subsets of kappa of size kappa that are pairwise almost disjoint. And maximal almost disjoint, or MAD, means that it's almost disjoint. It has to have size at least kappa, and it cannot be extended to any bigger almost disjoint family of subsets of kappa. You need this restriction that there are at least kappa sets in your family, because otherwise you have trivial examples, like you can partition kappa into 2 disjoint sets, and this would be a mad family, right? You want to avoid such examples. Okay, so and then you have the natural cardinal invariant associated to this notion. A kappa is the minimal size of a mad family of subsets of kappa. Okay, next we move to S. This is the splitting number. So we say that A splits B if B gets cut in two by its intersection with A and the complement of A. So B you look at the intersection of B with A, and you look at the intersection of B with the complement of A, and they both have to have size kappa, right? So B is getting cut in two. And a splitting family is just a family of subsets of kappa with the property that any element or any subset of kappa of size kappa is split by something in the family. It has to split every subset of kappa of size kappa. And S kappa is the cardinal invariant associated to this. It's the minimal size of a splitting family. Okay, so the next invariant is the ultrafilter number. So again, let kappa be a regular cardinal, infinite regular cardinal. So a base for a uniform ultrafilter on kappa just means that so it's a family of subsets of kappa, and you just close it upwards. You just close it upwards. You get a uniform ultrafilter on kappa. Uniform ultrafilter just means that every element of the ultrafilter has size kappa. So this is a base for a uniform ultrafilter on kappa. And U kappa is the minimal size of a base for a uniform ultrafilter on kappa. Okay, so then finally, so I've defined 5 invariants so far. The last invariant is P kappa. I'm not going to say a lot about that. So, I'll just give the definition. So you have take two subsets of kappa. This now means that A is contained in B modulo a set of size less than kappa. Okay, and a centered family, a family of subsets of kappa is centered for any subfamily with size less than kappa, the intersection has size kappa. Right? In the case of omega, this would just mean that if you take finitely many things, their intersection is infinite. Now you just generalize everything to kappa. Pseudo intersection, kappa pseudo intersection, means that so take a family of subsets of kappa. A is called a kappa pseudo intersection if it is contained in all the members of F modulo a set of size kappa in this sense. Right? And P kappa is the minimal size of a centered family which has no kappa pseudo intersection. I should say maybe here that it's not actually clear whether this is the right generalization of P to kappa. You could also, for example, look at the forcing axiom for kappa-centered posets or things like that. I mean, it's not really clear whether this is really the correct generalization to kappa. But anyway, not worry about that now. Well-known fact. So I should say, so I've defined these 6 invariants. I'm going to try to give some background and the questions that motivated our work, but I'm not going to try to give an exhaustive survey of all the things that are known, right? I mean, a lot of things are known about all these invariants. It's a long list of results. I'll try to present only some of the highlights. So it's a well-known fact that the cofinality of B kappa is at least kappa plus, and B kappa must be regular and less equal the cofinality of D kappa, which is of course bounded by 2 to the kappa. And it's a theorem of Cummings and Shelach that for any regular kappa, so kappa is infinite regular, this is the best possible you can do in ZFC. For omega, this was known long time ago. This was by Heckler for omega. But for uncountable kappa, Cummings and Shelach did this. Okay. All right, so let's now move on to B and S, the connection between B and S. B omega and S omega are independent of each other. But if you look at uncountable regular cardinals, you actually get they're not independent anymore. So there are 3 attributions here because there are sort of 3 different claims. One is that consistently B omega is less than S omega, and that was done by Shelach actually. And then there is consistently S omega is less than B omega. I believe that's due to Baumgartner and Dordo. I'm not completely sure, but I think that was done by Baumgartner and Dordo. And this fact for regular uncountable kappa is an earlier paper of myself and Saharon. This is like folklore. I mean, S omega being less equal D omega. Okay. So, 1 minute. Yeah, okay. So, and then, okay, the connection between B and A, it's a folklore result that B omega is less equal A omega. Shelah produced a model where B is aleph 1 and A is aleph 2. And it's an unpublished result of Blas, Hittin, and Zhang that if this is for uncountable kappa. This should say kappa greater than omega. If kappa is greater than omega, then d kappa equal kappa plus implies a kappa equal kappa plus. This is open for omega. Okay, for omega this is open. So the hypothesis here should say kappa is greater than omega. Okay. So you could ask whether there is an analog of this Shelah theorem at uncountable regular cardinals. For example, is it consistent to have B kappa equal kappa plus and A kappa equal kappa double plus? And this shows that cannot be done. So I mean, omega is the only cardinal for which the only regular cardinal for which you can prove the consistency of this statement here: B kappa being kappa plus and A kappa being kappa double plus. If you take an uncountable regular cardinal, then B kappa equal kappa plus actually implies A kappa equal kappa plus. So this is, so it's sort of interesting that in both of these results, omega is sort of the oddball, right? It's all the uncountable regular cardinals, you get a ZFC theorem. But for omega, you get an independence result, which is what you might not expect, I don't know. Okay, so now we move to D and A. So it's a sort of well-known result of Shelah, I think from the early 2000s, maybe 2000, that D omega is consistently smaller than A omega. And this result was sort of the starting point for our work. So he actually gave two different proofs of this result. One proof was using ultrapowers. You have a forcing, and or rather you have some forcing iteration, and you repeat the process of taking ultrapowers of this by some kappa complete ultrafilter. So that needed a measurable cardinal, and then later he managed to eliminate the measurable cardinal and gave a proof just from the consistency of ZFC using some method called the method of templates. I'm not going to say what that is because I don't really need it. One of the sort of limitations of this method, both of these approaches, both the approach of using ultrapowers and the approach of templates, was that they you generally need to assume that the forcings that you're using are definable CCC forcings, like Suslin CCC posets, like Diego was talking about just now. Or that they're absolutely CCC. For example, sigma-centered. You can use some non-definable posets, but they have to remain CCC after any CCC forcing. In general, if you want to use non-definable things like a Suslin tree, would not work very well in this framework. So one of the motivations for our work was this test question, right? So we wondered whether can you get D omega less than A omega, this result, but as much of Martin's axiom as you can possibly have with that restriction. So MA for posets, all CCC posets of size less than D, plus this inequality. This was actually the original motivation. This is how everything started. This is how this stuff started. Okay, so this was actually not a motivating question, but we managed to answer it anyway, so I will talk about it. So there are several proofs of the consistency of B omega less than S omega. The original one was given by Shelah, like I said. This was this Baumgartner-Dordal thing. But then later, for example, Brendel and Fisher, and I think also Diego and Fisher, they produced many different models where B is less than S and S is less than B. But in all of these models, A is either equal to S or B. So natural question you can ask is, can you separate, can you have B less than S less than A? This was not one of our motivating questions, but we're going to answer it, so I just thought I would put it there. Okay. Okay, on the other hand, this was a motivating question. Can you take this machinery that Shelah had in his work on the consistency of D less than A, and can you lift it up to higher kappa? right? So can you prove the consistency of d kappa less than a kappa or b kappa less than a kappa for uncountable regular kappa? Sorry? What? Oh, yeah. This inequality should be the other way around. Kappa should be. Sorry? It's either 0 or 1. Yeah. So, yeah. This should be bigger than omega. So, and this was sort of a test question for this paper 3 is Shalah's paper where he showed the consistency of d less than a. Okay, so by what I just said before, you would the minimal configuration where you could have something like this is that B and D are both kappa double plus and A is kappa triple plus. Okay, this is the smallest configuration. Okay, so then now about U and D. Yeah, this is a folklore result that B omega is less equal U omega, and U omega and D omega are independent. Now, I mentioned earlier that for uncountable kappa, again, kappa should be regular here. Uncountable kappa, it's a theorem that S kappa is less equal B kappa. Now, if you dualized this, you would expect D kappa to be less equal U kappa. But we don't actually know how to prove that. I mean, as far as I know, that's still an open problem. Whether, it is provable in ZFC that for uncountable regular kappa, D kappa is less equal U kappa. So, okay. But for omega, they're independent, just like S and B are independent. Okay. I should probably also have put Goldstone Shalah here, right? I mean, they produced this model where D is less than U. Is that right? Yeah, something like that. Or R is less than U. Yeah, okay. So I should have put at least one, their paper here. Anyway. Okay, so, and then in the same paper where Shalah showed the consistency of D less than A, he proved the consistency of U omega less than A omega, consistent to relative to a measurable cardinal. In this result, he did not manage to eliminate the measurable, right? So this is still an open problem whether in ZFC you can show the consistency of U omega less than A omega. Okay, so then there was some work of, for higher kappa, there was some work of Garty and Shelah, where they proved that if kappa is super compact, then it's consistent that U kappa is less than 2 to the kappa. This doesn't, there are good reasons why you probably need some kind of large cardinal here, but like for example, I think the analog of this at omega 1 is completely open. I will talk about that later. So another motivating question was, in the same vein as sort of you're generalizing the methods of Shelah, to larger cardinals. So at a super compact cardinal, can you get the consistency of U less than A? Yeah. Okay. So this is just something about P. I'm not going to say a lot about P, like I said, so this is just, let's see, I guess this is folklore that P kappa is less equal B kappa, and it's not hard to see that it's consistent to have P kappa less than B kappa for all infinite regular cardinals. Okay, so that's my summary of definitions and things that were known and motivating questions. Now I'm going to go to the summary of our results. So, any questions before we go there? Yes.
There is a continuation of the paper by Garty and Shelah.
Yes. Okay.
They consider many cardinal traits, but they all end up being small.
Oh, I see. Okay.
Can you say something more by your methods? Because they all end up being the same way with the
Yeah. We're going to answer this question here. Yeah. So then U and A will be different. Okay. So now we come to the summary of our main results. So the first sentence is the answer to a question that answers the first question that I had in one of the slides before. So it is consistent that to have MA below D and D less than A. By the way, so I should maybe say right at the beginning that all our results are relative to the consistency of a supercompact cardinal. Right? So we need a supercompact cardinal to begin with. Sorry? It sounds ridiculous, I agree, but this is life. Okay, so then this stuff is, it tries to say that we can parameterize the situation, okay? We can allow D to be various things, and we can allow A to be various other things. You don't have to worry about, I mean, so we need some cardinal arithmetic assumptions here. But if you assume, for example, that everything is regular and GCH holds in the ground model, you can forget all this stuff. You just start with a supercompact cardinal where GCH holds, and then you can do a CCC forcing extension in which you have MA below D, and D will be this mu plus, and then A will be, well, it'll be the cofinality of chi. Okay, so we can get this, so this is an answer to the first question I had. Okay, so we can also get the consistency of B omega less than S omega less than A omega. This was the second question. And this is also consistent relative to a supercompact cardinal, which, as Martin pointed out, is clearly ridiculous. But what can we do? And again, you can parameterize the situation. You can let B be various things, S be various things, and A be various things. I believe that it's possible to also get bigger gaps between B and S, but I haven't really checked that, so I don't want to claim something I haven't checked. But the gap between S and A can be big here. That's okay. This is again CCC, yes. This is again a CCC forcing. Okay, so that was the second question. The third question is, okay, so it's consistent to have D kappa less than A kappa, and this works for any regular kappa greater than omega. So for example, this works at omega 1. Right? So we can have a model where D of omega 1 is less than A of omega 1. But again, we need a supercompact cardinal, and again, we can parameterize this in various ways. Oh, yeah, there is probably one thing that I should point out in all of these results. This also applies to the previous slides. All these invariants end up sitting on top of this theta, right? So they're all very big from the point of view of the ground model, right? So, I mean, there is this theta, which is a supercompact cardinal, and then the B here is a mu plus, so it goes above the supercompact. That's also true in all of these results. Like, here D and B are equal to mu plus, which is above the theta. Theta is the supercompact cardinal. So they all end up being very large. Okay, so yeah, all right. So we can also separate more invariants. We can get P kappa less than B kappa less than D kappa less than A kappa. And again, we need a supercompact cardinal for this, and this again works at any uncountable regular kappa. Well, I guess it also works at omega. I mean, there's no reason for me to. But I guess that was probably known. So then, okay, so yeah, this again just parameterizes the situation. All right. Now for the U and A, this answers your question, Mirna. If you start with the Laver indestructible supercompact cardinal, so kappa is now a Laver indestructible supercompact cardinal, then you can have a model where U kappa is less than A kappa. But again, you need this so yeah, this is consistent relative to a supercompact cardinal that sits above kappa. So if you want to prove the consistency of U kappa less than A kappa at a supercompact, you need a supercompact above that, and then the value of U kappa will jump above the one that's above. Yes?
So the models here have kappas omega.
Yes.
What does the supercompact become?
Well, it can become, for example, the B. I mean, its successor will become B, for example. Like 1 minute. So, for example, here, mu could equal theta, in which case B of omega is just simply theta plus. So theta is the supercompact, and it is possible that mu is equal to, that's allowed here, I guess. And then B omega is just... is it okay?
Yeah.
All right. Okay. All right. So this is okay. So this finishes the summary of the results. Any other questions? All right. So now I'm going to try to sort of explain the definitions that go into these proofs, and some of the lemmas that you need. Okay. So Boolean ultrapowers have been studied by model theorists for a long time. They're a special case of limit ultrapowers defined and studied by Kiesler. Limit ultrapowers also show up in large cardinal theory, as we all know. They're extenders. Extenders are a special case of limit ultrapowers. There are closely related ideas in the work of Maliaris and Schellach. They use Boolean ultrapowers for something else. And there is another application of this approach of Boolean ultrapowers in a recent work of Goldstein, Kellner, and Schellach. Okay, so now I need to give some definitions. So theta and mu are cardinals. B is a complete Boolean algebra. So we say that B is less than mu, less than theta distributive. So that means that if you give me, let's see, fewer than theta many sets, each of size smaller than mu, then you can interchange the sup and the inf. Right? So these are, there are C many of these, so it's fewer than theta many of these. That's the less than theta. Fewer than theta many sets, each having size less than mu. Then taking all their sups and then infing them is the same as suping the infs of all the possible ways to choose one element from each of the sets. Okay, so that's distributivity. Okay, so okay, now I actually come to the definition of a Boolean ultrapower. You can define this for any model. So by the way, I should say that there is a different way to think about this in terms of the way a set theorist would think about it. Here I'm thinking about Boolean ultrapowers the way a model theorist would think about it, because I need to talk about realizing and omitting types. Okay, so let B be a complete Boolean algebra and let M be an arbitrary non-empty set. This Mac of B is just simply all the maximal antichains in B. And now I define this M of B. M of B is just a collection of all functions whose domain is a maximal antichain and its range is contained in the given set. So it goes from a maximal antichain into the model. I mean, you should think of M as a model. Typically for us, for all our applications, they will be purely relational structures. Our language will be completely relational. So you just have a bunch of relations on M, but for now it's just a set. And now suppose you had a filter on B, you could define an equivalence relation. Where what do you do? So when are F and G equivalent? So you have these two functions going from these two maximal antichains. So you take one element in this maximal antichain here, one element in this maximal antichain here. You ask, is F of A equal to G of B? And if they are, you take their inf, and you take the sup over all the pairs where they're equal. Does this make sense? So you have this. You have the domain of F, which is a maximal antichain. You have the domain of G, which is a maximal antichain. For any A in the domain of F and any B in the domain of G, you ask, is FA equal to GB? And when that happens, you inf A and B, and then you take the sup over all such pairs. And that has to be in the filter D, and this is an equivalence relation. Okay. Yeah. Okay, so we're primarily interested in, like I already said this, we're primarily interested in relational structures. Oh yeah, so I should also say that this is one difference between, okay, I'll come to that. We're generally interested in realizing and omitting types in L theta theta logic. Right, okay, so theta is some super compact cardinal. We're dealing with L theta theta logic, and we're interested in omitting and realizing types in that. And we're primarily interested in relational structures. So M will just have several relations of arity less than theta defined on it. Okay, and so what is the overall goal? The overall goal is to build a Boolean algebra B, to build a theta complete ultrafilter D on B, so that the Boolean ultrapower is saturated in some suitable sense. Okay, in some suitably defined sense. So we want to find a B like this, and we want to find an ultrafilter D like this, which is theta complete, and moreover, the Boolean ultrapower is suitably saturated. Okay. So how do you define the interpretations of the relations? Let me just also say this. So you have a model, right? So you have M, and then you have some relations defined on this. So theta is any cardinal, and B is any complete Boolean algebra. So M is this non-empty set. I'm thinking of the relation as consisting of functions from this set X into M. Okay, so X is the index set on which my relation is defined. It is some subset of theta of size less than theta. So you can think of that as the coordinates where the relation is defined, and the relation is some subcollection of m to the x. Okay, so like any relation, but it has arity less than theta. So D is your filter on B. Then R to the B slash D, or mod D, is the following subset of m to the b to the x. So suppose I give you a function in m to the b to the x. So what does that mean? If you give me any, let's say, zeta in x, f of zeta belongs to m to the b. Okay, so its domain is a maximal antichain. Right, the domain of f of zeta is a maximal antichain. So for every zeta in x, I have f of I can pick one element from all these maximal antichains, and I ask, does this sequence belong to the original relation? You see, this makes sense because this thing is now a function from x into m. Right, zeta is in x, so f zeta is in m to the b. So domain of f zeta is a maximal antichain, and f zeta is a function from this maximal antichain into m. So if you give me a sigma of zeta which belongs to this maximal antichain, I can see this thing is now an element of m. F of zeta, sigma zeta is some element of m. So this is a sequence in m to the x, and I ask, does this belong to R? And if it does, I take the inf of all those elements, and then I take the soup over all that stuff. Right? This is the, in some sense, the truth value of the relation R at this function f. And this function f is an R to the b slash d if its truth value belongs to the filter D. Okay? Okay, so you can define interpretations of functions and constant symbols, but we do, that doesn't matter to our applications. So there's an obvious analog of Walsh's theorem here. You just sort of generalize this. Instead of looking at relations, you look at an arbitrary L theta theta formula now, right? And you have a sequence of functions, and you can do the same business there, and then you get that holds in the Boolean ultrapower if and only if its truth value is in D. But to prove that we need some kind of distributivity. This is just worth noting. So to prove this analog of Walsh's theorem in the L theta theta context, you need to know that your Boolean algebra is the mu is just arbitrary here. You need to know that the size of its maximal antichains and the distributivity sort of are the same. Okay. So the typical case we'll deal with is theta is super compact. Mu is something bigger equal theta, and B is a mu plus CC less than mu plus less than theta distributive. Complete Boolean algebra. I guess I should say that. B is a complete Boolean algebra. D will be a theta complete ultrafilter. Okay, so now I come to an important point, which is that unlike in the first order case, since you're taking an ultrapower by a theta complete ultrafilter, you have no hope of realizing all possible types, right? You will never make the model really saturated. So here, for example, if you take the ordinal theta and you take its Boolean ultrapower, this will be isomorphic to some ordinal. It will be well-founded, right? Because you have a theta complete ultrafilter. So it will be isomorphic to some ordinal. It will be bigger than theta because, I mean, this is really like J of theta, right? I mean, you get an elementary embedding, right? And this will be like J of theta, so it will be some alpha greater than theta. And now you just look at the simple type, look at all the things that are above anything in, that are above, I'm not sure that this makes sense. Yeah, that's right. Yeah. So I'm just saying that you don't realize this type, and this is actually a small type. Right, it has only size theta, and you're never going to realize this. This is a type of size theta which is always going to be omitted. Huh? No, the Boolean ultrapower. Right, because this is an ordinal, so there is nothing. I mean, this is just saying that there is something that is above that is below theta, but is above everything less. So theta is not below theta, and
X is the variable.
yeah. It has to be x has to be less than theta. I mean, I guess I forgot to say that. Okay, so we can only realize certain very special types of size less equal mu, but actually for our applications we will need to realize some types of size greater than mu also. But you need to put lots of restrictions on these types. Yeah.
Isn't that getting realized? I mean, you want something like smaller, like below the critical point. You want something to say that there's a non-standard number.
Add the formula x less than theta.
I mean, but that doesn't make any sense because that's outside of the money. That's not in the language. Like theta is not in the language.
No, but it is in the ultrapower. It's a parameter in the ultrapower.
But what is your language?
The language just consists of less than. But you're allowed parameters, any parameters coming from the ultrapower. So yeah, I have to add the formula x less than theta. I mean, and theta is a parameter, right? I mean, that's in alpha. It lives in alpha. It's a constant. It's an element of alpha, so I can use it as a parameter. So that would just. I mean, if you could realize that would say that alpha is not an ordinal. I mean, it's right. So of course there are simpler examples, right? I mean, I could have just taken a decreasing sequence. The type of.
I think it kind of becomes more clear if you describe something which is less than omega and greater than all the natural.
Sure, for example, I mean, non-standard natural numbers or a decreasing sequence of ordinals, right? I mean, you will never realize such a type. So you have to realize, so you have to restrict yourself to some very special types. This is somehow easier to do this when the size of the type is less equal the chain condition here. I should say less than the chain condition here. And it becomes harder when the size of the type is bigger. And then you have to put more restrictions on the type. Okay, so I will deal with the easy case first. I'll say how we do that. The easy case meaning when the size of the type is small, it's less equal mu. So this is related to what Marianthi was talking about in her talk. It's about finding multiplicative refinements using regular ultrafilters, but on a Boolean algebra, in L theta theta logic. So B is a complete Boolean algebra. Mu and theta are cardinals. So D is mu theta regular. Okay, so if there is a sequence of elements in the ultrafilter and there is a maximal antichain with the following properties. Okay, the size of the maximal antichain is no more than mu. That's the parameter mu. And okay, so for every alpha less than mu and for every d and I, you want that you basically want that this maximal antichain supports the elements here. If you sort of think of B as being the completion of a forcing, that says that the supports of your this condition 2 is basically saying that your I is sort of supporting all the things in D. So for every alpha less than mu and every d and I, either d is below C alpha or its inf with C alpha is empty. So every element of C alpha is simply the soup of all the things in I that are below it, right? Because I is a maximal antichain. So you just take all the things in I that are below C alpha and you take their soup and you will get C alpha back. And for every d and I, this is probably the most important condition, the condition 3. There are only a small number of things below C alpha. That's the theta here. Right? The number of things below C alpha is small. Okay, so and then you can prove that these things exist. So suppose theta is regular and mu to the less than theta is mu, and B is any complete Boolean algebra, and take any maximal antichain of size mu. Then there is a sequence C alpha and a theta complete ultrafilter D, such that this pair witnesses that D is mu theta regular. So you always have lots of these regular.
It's not written, but it's meant.
Yes. Well, no, I mean, yeah, it's meant. But you can just extend this to an ultrafilter, and that doesn't damage the regularity in any way. This is just, if a filter is regular, then any superfilter is also regular. Yeah, but I mean, if you have a large enough cardinal, you don't care. Okay, so this terminology moral problem we took from the paper of Maliaris and Shelah. But I think they mean, I'm not completely sure, but I think they mean something slightly different from what we mean. Okay, so suppose upsilon is an ordinal and D is a theta complete ultrafilter on B. We say that B bar is an upsilon theta BD moral problem. When, okay, so this is a sequence indexed by subsets of upsilon of size less than theta. Okay, B of U is in D for every U in which is a subset of upsilon of size less than theta, and it's monotonic, which means that if U is a subset of V, then BV should be less equal BU, and B of the empty set is just 1. I mean, this is just for convenience. This last thing. Okay, so this is and realizing types, at least small enough types, corresponds to finding multiplicative refinements of such things. So let me say what is a multiplicative refinement. So you say that B bar prime D solves B bar when, okay, so it's also a sequence like B bar. So it's indexed by subsets of upsilon of size less than theta. Everything is in D, okay, and it's multiplicated. That just means that, okay, so for any U of size less than theta, if you write it as a union of less than theta many sets, actually I could have put singletons here. That would have been clearer. I could have just put singletons here. But if you write U as any union of fewer than theta many sets, then B prime of U is simply the inf of the B prime of the U zetas. Okay, so this is the multiplicativity. And then it has to refine B bar, so it has to be below B prime of U must be below BU for every subset of upsilon of size less than theta. Okay. Oh, I see. Okay. So if I don't require that B prime of U is in D, but simply that it just be non-zero, then instead of D solves, you just say solves. I mean, that's some I mean, I'll need that probably for some later definition. That's why I have it. Okay, so how are we going to realize a type? So what do I mean by a type in the Boolean ultrapower? I just mean a collection of formulas now. These are now L theta theta formulas. I didn't say that, but they're L theta theta formulas. And we allow parameters from the ultrapower. Right? So you're allowed to have parameters that come from the ultrapower. Those are the F alpha bars. Okay? So it's just a collection of formulas such that any collection of size less than theta is realized in the Boolean ultrapower. Okay, so given a type, you can translate it into one of these moral problems. How do you do this? So suppose you have a type. Suppose I give you and the type, let's say, is indexed by upsilon. So you have phi alpha less than upsilon. If you give me a subset of upsilon of size less than theta, I can simply take the truth value of this formula. There exists an X such that it satisfies all the things in U. And this will be in D because of the assumption that any subset of size less than theta is realized. Right? So this truth value will be in D. And you can easily check that it satisfies all the conditions I had for a model problem. And then now, if you have okay, so this is one of the important lemmas that we use, which is that if you have a theta complete mu theta regular ultrafilter on B, if you have a theta complete mu theta regular ultrafilter on B, and this is the most important requirement here, namely that upsilon is less equal mu, so it's a type that's not too big, you have a type of size upsilon, then the following are equivalent. The type being realized is the same as the translation. The translation meaning this is the translation I did here by taking BU to be the truth value of this formula. That's what I mean by translation. This translation is this thing. So the translation has a D solution in the sense that I defined before. These are equivalent. The type being realized and okay. I'm sorry. I can,
It
yes.
seems to me there is another translation behind it.
Uh-huh.
The language of sensing.
Uh-huh. Yes.
Forcing language, yes?
Yes.
So this looks like the forcing thing, right? Remember, it's a knife and then the jig.
I don't see a direct connection because I mean you need this dissolution. I don't know of any analog of that in forcing. Finding a multiplicative refinement for a monotone sequence. I don't think there's. I mean, as far as I know, there's no direct analog of that in forcing. This is like good ultrafilters, in model theory.
Yes, but I thought the dissolution was like counting something.
Yeah, but then you have to find this multiplicative refinement, which is, I mean, as far as I know, there's no real analog of that in forcing. I mean, sorry? D isn't generic, it's just some ultrafilter. Okay, so this will not work if your type is bigger than mu, okay? But for certain very special types of size greater than mu, why do we need this? Why do I keep harping on this, mu being bigger than, epsilon being bigger than mu? Because we need this when we try to prove that A is large in our models. We need to realize some type which is very big, right? Much bigger than mu. That's how you make A large, by realizing a certain large enough type. Okay, but then there is some modification of this which can be made to work, which I'm not going to talk about because it's a bit technical. Okay, so let me just finish. I'm almost out of time, so let me just finish by explaining what is the Boolean algebra that we use, right, in all our applications. It's a very specific Boolean algebra. It's simply the completion of partial functions from chi to mu with support less than theta. Okay, this is just adding subsets of functions from a generic function from chi to mu using conditions of size less than theta. Ordered by reverse inclusion, we take the completion. This is the Boolean algebra B on which we build the ultrafilter. Of course, this is not what we force with, right? I mean, this is just where D is going to be. And then we have some other forcing, and then you take the Boolean ultrapower of that forcing by a theta complete ultrafilter on this Boolean algebra. And then you have to show that various types are realized. Let me see. I think I just have a couple of minutes. Okay, I think I will. I think I will skip this part and go directly to the questions. So this is the Boolean algebra we use, and we. How do you? This thing doesn't work. Sorry? Click. Okay. Okay, so I'll just go directly to the open problems. Okay. No. Yes. Okay, so there are many open questions. For me, one of the most interesting is this on omega. As far as I know, it is unknown relative to anything, super compact cardinal, whatever you want, whether B less than S less than D is consistent. Okay. As far as I know, maybe this has been solved, I don't know. And I also don't know how to put A in the middle. I said we have this model where B is less than S is less than A. But I don't know how to put A in the middle, but maybe Diego's methods can answer this. I don't know. No? Okay. Well, what about the first one? Can you get B less than S less than D using your method? No. Okay. All right. So these are both open then, I guess. Okay, so this is related to what I said about all the cardinal invariants in our models being really large. They're all above a super compact cardinal, right? So you can ask, so we have a model where B is less than S is less than A, but can you make them Aleph 1, Aleph 2, and Aleph 3 instead of, some former successor of some former super compact cardinal? And of course, can the consistency of B less than S less than A be proved without large cardinals? This MA question, okay, this is again in the same vein as this. We can have MA less than D and then D less than A, but But again, the cardinals are really big, right? They're not LF1 and LF2 and LF3. So that's how that's the purpose of this question. So in other words, if you assume MA LF1 and that D is LF2, then can you prove that A is LF2? If not, then you would have this model where D is LF2 and A is LF3, I guess, and then MA LF1 holds. I don't know the answer to that. Okay, now going to higher cardinals. Again, can we have D is LF3 and A is LF4? This is the smallest consistent situation, right? I mean, if D is LF2, then D of omega 1 is LF2, then A of omega 1 is also LF2. So this is the smallest consistent situation. Of course, can you prove all this without large cardinals? And then there is an old problem of HUN-REN about U just on omega 1. So is it consistent to have a uniform ultrafilter on omega 1, which is generated by fewer than 2 to the LF1 many sets? That's all this is asking. Okay, so here are some references. Thanks a lot.